Hi, everyone. My name is Michael Fisher, and I'm with Amazon Web Services. I'm a Principal Specialist Solutions Architect focusing on EC2 Graviton. And I'm here to speak with you today about how you can run your container workloads with AWS Graviton. First, I'm going to start talking today about what Graviton is. I'll also be talking a little bit later about how to build containers for Graviton and how to deploy containers for Graviton. I'll also show a demo which shows how to deploy containers and build images using a code pipeline as part of the DevOps automation process. I'm really excited to talk to you about Graviton today. Graviton is a custom processor that has been built in-house by AWS as part of our Annapurna team of engineers. Graviton is a custom AWS silicon with 64-bit processor cores. These are some of the most advanced CPU technologies in the industry today, and is available exclusively on AWS as part of EC2 and some of our managed services as well. Graviton has been built with the cloud in mind. And so our engineers at Annapurna have built Graviton by looking very closely at how customers actually use the cloud today. And so we've targeted our optimizations in these processors for cloud-native workloads. And we've done so while also leaving unnecessary features of the CPUs out. Graviton is part of our overall Nitro system, which allows us to rapidly innovate, build, and iterate on customer behalf by taking their input into account and how they run real workloads in AWS. So we can do so in a cost-effective, sustainable, and performant manner. Graviton allows our customers to achieve much lower total cost of ownership simply by switching to Graviton-powered instances. There are three ways in which customers achieve lower total cost of ownership with Graviton-powered instances. First, Graviton provides the highest performance for the instance family on a generational basis. It does so by utilizing custom instructions and some of the best engineering that you can find in CPU technology today. In addition, customers achieve lower TCO simply by nature of the fact that when compared across instance generations, Graviton is 20% lower price per hour than comparable x86 instances in the same generation. And this lower cost can be seen generation over generation. What does this mean? This means a total cost of ownership of up to 40% better price performance versus comparable x86 instances. We're really proud of what we've been able to achieve with Graviton, and our customers have told us that Graviton provides real-world savings in total cost of ownership. So to demonstrate some of the performance gains customers can see with Graviton, we've set up a few different tests of real-world workloads. One example is load balancing with Nginx. We've compared a load balance setup with Nginx on M5 x86-based instances and then tried to run the same workload on our M6G Graviton instances. You can see here that in terms of requests per second, we can see a 24% difference, 24% faster on M6G instances versus our M5 instances. This is real-world performance that Graviton unlocks. Next, we benchmarked memcached, which is a very common memory-based cache implementation that's used commonly among our customers. With memcache, you see a 43% improvement in terms of requests per second for M6G versus M5. Again, real-world performance improvement. The next important thing to discuss about Graviton is sustainability. Amazon has signed the Climate Pledge, in which Amazon is aiming to significantly reduce its carbon emission targets and also reduce its overall energy used over the coming decade. By introducing Graviton 2, we see performance power efficiencies up to 3.5 times better performance per watt. Basically, this means that for each unit of work that a Graviton 2 processor does, it uses 3.5 times less energy to do so. This means that the instances use less power, and it also means that we can actually install them in our data centers with much higher density. Overall, this leads to a significant improvement in cost and a much lower carbon footprint. With Graviton 3, we've continued on this trend, and we made them 60% more energy efficient over comparable EC2 instances in the same generation. And we've built a tool that you can access via your cost and usage reports and the billing console. It's called the Carbon Footprint Tool, and you can access it in your AWS account simply by going to the billing console. I've left the links here for you to take a look at so that you can see it for yourself. Now we have Graviton instances for every workload that customers have brought to us. And we know not every customer runs the same workload and requires the same features from instances. And so we've created a large portfolio of Graviton instances across 2 different generations. And we're now in our 3rd generation of Graviton instances. To start, our C6G and C6D instance families are designed for compute-intensive workloads. Our M and M6G instance families are for general purpose workloads, and they have a little bit more memory than per virtual CPU than the C6G family. The R6G, R6GD, and X2GD families have even more memory installed, with X2GD having the most memory installed for the Graviton instance families for Graviton 2. We also have storage optimized instances, including IM4GN and IS4GEN. These instance families have terabytes, up to terabytes of NVMe powered instance storage using our latest Nitro NVMe storage hardware. Nitro SSD is our newest family of SSD technology with significant improvements in performance and much improved tail latency compared to earlier generations of our SSDs. With IM4GN and IS4GN, customers can have sustained improved performance with a very low latency variance. Finally, we have our G5G instance type, which is the first instance family for Graviton that includes a NVIDIA GPU. With G5G, customers can do Android game streaming and cost-effective ML inference as well. T4G is our burstable instance type that's best suited for customers who need burstable CPU, but use more memory or depend more on memory or network throughput than constant CPU utilization. And until December 31st, 2022, you can have customers can have T4G small instances for free for up to 750 hours a month. Finally, our newest instance type is the C7G family, and that's based on our newest generation of Graviton processor called Graviton 3. Graviton 3, which is now in 4 regions, provides up to 25% better compute performance, up to twice as fast floating point performance, and up to twice as fast cryptographic workload performance compared to Graviton 2. Overall, Graviton 3 provides up to 3 times better performance for machine learning workloads, including support for the bfloat16 instruction. Graviton 3 is also the first in the cloud to feature DDR5 memory that provides up to 50% more memory bandwidth compared to DDR4 memory. Next, I'd like to turn to containers on Graviton, which is what you're really all here to learn about. Containers is one of my personal favorite technologies, as I was formerly a container expert with AWS as well. Graviton provides broad support for containers. The orchestrators support Graviton, all major orchestrators support Graviton, including Amazon ECS, Amazon EKS, Docker Swarm, and Kubernetes. All major image registries support Graviton as well, including Amazon ECR, Docker Hub, Artifactory, and Quay. Container-optimized Linux distros that support Graviton include BottleRocket, which is AWS's custom-built container-optimized Linux distro, which provides very high security and a small footprint. With BottleRocket, it's been solely designed to run containers and has left out all the unnecessary features and improved security by having SE Linux, the security layer for the Linux kernel, enabled by default. Flatcar Linux also is available as well. And of course, you can use general purpose container Linux distros such as the EKS and ECS optimized AMIs or Amazon machine images that are provided by the ECS and EKS teams. Those also work with Graviton as well. And if you'd like to run your containers serverlessly, both AWS Fargate and AWS Lambda provide Graviton support as well, with similarly low cost compared to x86, Fargate, or Lambda, and higher performance as well. I'll talk about serverless a little bit later as well. There's also broad Graviton support in the overall DevOps ecosystem. In the DevOps ecosystem, I like to break these into three categories. On the fully managed side, by fully managed, these are DevOps pipeline orchestrators that actually provide managed compute. So not only do they provide the logical framework for building your DevOps pipelines, including running tasks, setting variables, and so forth, and declaring stage dependencies, but they also provide compute that you can immediately run your DevOps tasks, your build and deployment tasks on. AWS Code Build, for example, provides managed compute for build, deployment, and test processes. And it supports Graviton simply by declaring a Graviton image and compute type. Circle CI also provides runners that are ARM64, as does Cirrus CI and Travis CI. Circle CI, Cirrus CI, and Travis CI are managed services that are provided by those companies. Then there's the hybrid approach. In a hybrid approach, a managed service provider such as GitHub, BuildKite, or GitLab manages the pipeline orchestrator, but you bring your own compute in terms of runners by registering them with the respective service. GitHub, BuildKite, and GitLab all support Graviton 2-based runners. If you're running your runners on ECS, you can even use Fargate to attach them to those different runners, particularly GitHub. Finally, self-managed, Jenkins is the one most commonly used by our customers. With Jenkins, you can run either the master or the runners on AWS Graviton. All right, let's talk about what it actually takes to build a container image for Graviton. So one question customers often ask me is, can I actually build my container image for Graviton and run it on AWS? And the answer is most often yes. The question really is, how much work do you have to do in order to be able to achieve that? And the answer is really going to depend on how your application is written. If your application is written in a pure scripting language, such as Python, PHP, Perl, or Ruby, or Node.js, you can actually typically simply copy your scripts into the build image and utilize the particular runtime, such as that's already been compiled for ARM64. This is typically a very easy process. And the same is true for pure Java. In many cases, for pure Java that does not have any native dependencies or rely on JNI, you can actually copy your jar, build your jar on x86 and copy that jar into your Docker image while building it, and it will actually run on Graviton just fine. But it's important to look for things like JNI or shared objects that might be used by your scripting languages. Typical cases in which you might find shared objects include accelerated math libraries, machine learning, graphics manipulation, video manipulation and encoding, and so forth. So look for files ending in .so or look for JNI being used in your jar. In those cases, you often have to recompile those shared objects or build them natively on Graviton. For the most common open source projects that utilize native objects, those are often easily recompilable in using Graviton and targeting the ARM64 architecture. A little bit more involved is for applications that are written in compiled languages, such as C or C++, Go, or Rust. In those cases, you'll need to either compile them natively or do cross-compilation. If your application is written in .NET, if it's already using .NET Core or a recent version of .NET, I believe .NET 6, you can often take the file and run it on ARM64 without any issue. However, if you're running an older version of .NET, you'll need to convert it to the newer version first. And as for Microsoft Windows, at the moment, Windows Server is not yet available for ARM64. As a general rule, the more current your software stack is, the easier a time you'll have using Graviton. So how do you start using containers on Graviton easily? Well, the first step is actually to start with a compatible base image. There are hundreds of compatible base images that are already prepared and ready to run on Graviton. Taking a look here at our Amazon ECR public gallery, we actually have an architecture filter in the bottom left of the screen. You can see here that by ticking the box that says ARM64, it will actually return a list of repositories that are compatible with Graviton. You can see here just a few examples in the screen, including the CloudWatch agent base image and the Datadog agent base image. But there are hundreds and thousands more, and you can simply search in the upper right, find artifact repositories box, and all major base images, such as Amazon Linux 2, Ubuntu, Debian, and Alpine Linux, all have ARM64 base images, as do many software application repositories, including Nginx, OpenJDK, Amazon Corretto, Java, and so forth. You shouldn't have too much trouble finding a compatible base image that works for you. Similarly, if you look in Docker Hub, it also has an architecture filter for base images. You can simply click on the ARM64 box here, and it will reveal those base images that are compatible with ARM64. I did a little search here for Ubuntu in the search box, clicked ARM64, and you can see here just a few examples of some base images that are available for ARM64, including Ubuntu itself, a version of Ubuntu with the Nginx proxy installed, and a version of Ubuntu with the Prometheus Cortex database installed. Again, you should have very little trouble finding a compatible base image. Once you've started with a base image, then you can begin to build your container image containing your application. And there are three ways to do this. The first way, which is the fastest way, is to compile your application natively on Graviton. And there are two major ways of doing this. You can either install your, actually three ways you can do this. You can install your Docker and Engine on a Graviton instance, or if you're using an Apple Mac with Apple Silicon available, for example, the M1 or series of processors or the latest M2, you can install Docker Desktop on this Mac, and you can actually build your container image for Graviton locally and quickly. You can also use AWS Code Build or a CI runner available from one of our partners, such as Circle CI, Travis CI, or Cirrus CI, and build it there on a compatible ARM64 builder. You can also remotely control a Graviton instance through BuildX via Code Build itself, or by attaching a CI runner to either a fully managed or hybrid CI/CD platform such as GitLab or GitHub. The next option is to cross-compile your software. With cross-compilation, you're actually building your application for Graviton, but on a different architecture. For example, if you have an x86 laptop running Windows or Mac OS, if you install the proper cross-compiler, you can actually compile to an ARM64 target on an x86 host. If you're building C or C++, there are cross-compilers available for most Linux distros. This includes GCC and CLang, which comes with the LLVM toolkit. Both GCC and CLang have options allowing you to specify an ARM64 target. If you're building in a very modern language environment like Go or Rust, cross-compilation is built in to these two environments. If you're using Golang, you can simply set the GoArch and GoOS values to the appropriate values. These are environment variables. Or on Rust, you can use cargo build and specify the -- target option to target the ARM64 architecture. Cross-compiling works at near native speed for compiling applications. Once you've cross-compiled those applications, you can actually start with, you can actually build your Docker image by starting with an ARM64 compatible base image, even if you're doing it on an x86 instance. And then during the build process, you can copy those foreign binaries into the image during the build process. Most Docker commands work in the cross-compilation scenario, such as env, from, user, entry point, cmd, etc. But what you can't do if you are building a Docker image on a foreign architecture natively is to call the run command, because you can't run ARM64 binaries in a container on an x86 instance. Finally, you can use Docker BuildX. Docker BuildX allows you to use your x86 hardware to perform all Docker build stages, even though the target is ARM64. And it does so by using the QEMU project to enable ARM64 in software. With Docker BuildX, you can actually compile your software inside the container image building process. So if you install GCC or other build development tools as part of your build process, using, for example, a multi-stage build, you can actually successfully do this with Docker BuildX. However, CPU emulation in software is not nearly as fast as doing it natively, or even as fast as cross-compiling. And so it's best for containers requiring a minimal amount of compilation in order to build the image. For maximum flexibility, AWS recommends building multi-arc or multi-architecture images. A multi-architecture image is an image that has support for multiple architectures. In this case, x86 and ARM64. And it works out of the box. And all multi-arc images work out of the box with all major container runtimes. This includes Docker on ECS, Docker or Containerd on EKS, and so forth. The runtime will automatically choose the correct image layers to pull based on the architecture on which it's running. And it's supported, and multi-arc images are supported by all major container registries, including Amazon ECR, Artifactory, Docker Hub, etc. I wanted to show you a little bit about how multi-architecture images work. It's fairly easy to create multi-architecture images. The easiest way to do so is to use Docker BuildX. I mentioned Docker BuildX before, and how it can be used to build images on a foreign architecture through software emulation. To use Docker BuildX, there's an initial step you have to take of actually creating a builder. So you would run the Docker BuildX create command. And here I'm giving the builder a name of multi-arc, although you could give it whatever name you want. And the next step is to invoke Docker BuildX build. The important arguments you give to Docker BuildX build are the list of platforms. In this case, I'm building it for Linux AMD 64, which is the x86 architecture, and Linux ARM64. I'm also tagging the image and pushing it at the same time. Docker build x build will do software emulation if the platform target is different than your host, and then it will use software, and it will run it natively if the build architecture is the same as the host. So if I were running this on my Mac M1 here, it would build my ARM64 image natively, but then use software emulation to emulate the Intel processor or x86 processor. And vice versa if I were running it on a Windows machine running Intel. The build process takes place in parallel to take advantage of multiple CPUs on your build instance or laptop. And then once that's done, the images are pushed to the registry associated with your tag. However, this process is not the fastest process. And so what we recommend is a multi-arc build pipeline. And in a multi-arc build pipeline, which I'll show on the next slide, we take advantage of build hosts, one for x86 and one for Graviton, that use native compilation in order to build each image very quickly and also test them as well. Once we've built the architecture-specific image, then we stitch them together with the Docker manifest tool. So here you can see a diagram of what a multi-arc build pipeline looks like. It contains 4 stages. The first stage on the left is the push to the code repo. This is what kicks off the build pipeline, or source stage, as it were. In the next stage, it consists of 2 parallel actions. In the top action, in the top action, you can see that the first step is to build and push the image on an x86 build host. And then once the build and push is complete, the full automation test suite is run on an x86 deployment target. In the action below, which is run in parallel, the same build and push steps are taken, except this time on a Graviton or ARM64 build host. Once the build and push is completed, it too is tested, this time by deploying it to a Graviton build host. These are done in parallel, and once both parallel steps have completed, only then will the multi-arc manifest build be created, and that's done in a separate stage. In this case, we're using code build as our execution host for it, but you can use your own execution hosts as well, or those provided by a fully managed CI/CD provider. Once the multi-arc manifest has been created, then you can deploy to your actual deployment targets, whether it be QA, production, etc. Of course, we always recommend deploying to a lower environment, performing additional integration tests before deploying to successive higher environments. So how do you then actually create the multi-arc manifest once you've built the architecture-specific images? Suppose that through our build pipeline, we've created 2 architecture-specific images, one for ARM64 and one for x86. And during the build stage, we have appended ARM64 and x86 to our tags. In this case, I have an app called My App. The version number comes from a Git reference, and it's ABC1234. And for the architecture-specific images, I've appended the architecture name to it. Well, from there, I can actually use the Docker manifest create command to build the multi-arc manifest. The first argument is the actual name of the architecture independent manifest. This is the one where we simply omit the architecture suffix. So in this case, it's my app ABC1234. And then the remainder of the arguments are the architecture specific image tags, the ones ending in ARM64 and x86. As a result of this create operation, I get a multi-arc manifest that looks like the JSON I showed in a previous slide. Once the manifest has been created, I then push it to my repository by simply pushing the image tag that is the multi-arc manifest. Once my multi-arc manifest has been built, or even if I were deploying 100% to Graviton, it's then time to deploy the image. As I said before, all major runtimes and all major orchestrators work seamlessly with Graviton, including ECS, EKS, and Docker Swarm, and so forth. Multi-arc images give you the maximum flexibility. With multi-arc images, you can choose the EC2 instance that works, or instance family that works right for you based on price, performance, and feature set. So with ECS, the control plane is architecture independent. The control, and both x86 and Graviton instances can join the cluster. You can schedule tasks on specific images via placement constraints and capacity provider strategies, which I'll show on the next slide. A placement constraint is a rule that filters out which container instances, which EC2 container instances are qualified to run the specific task or container. A capacity provider strategy routes a task to a specific EC2 instance, autoscaling group or instance. And if you're running your containers on Fargate in the serverless method, you can actually set runtime in your task definition. You can set the runtime to CPU architecture in the runtime platform to ARM64. At AWS, we highly recommend using Fargate for your capacity in ECS. Fargate is by far the easiest way to run containers on Graviton because it's completely serverless. With Fargate, you simply declare the number of CPUs and the number of memory resources that you need to run your application. You set the CPU architecture, and then you can begin running tasks in the most secure and scalable way possible on ECS. Fargate reduces total cost of ownership of running containers on ECS by removing any need to run EC2 instances yourself. So you don't have to worry about securing instances, running instance security agents, running any sort of compliance utilities or anything like that. And Fargate has a number of certifications available, which you can find on our website. With Fargate, each ECS task or container runs on its own separate, secure, protected instance, and nobody can log into it, not even AWS. Let's take a look here at an ECS task definition that runs on EC2 with a placement constraint. If your image is architecture independent, you may not need this. But if you're planning on running exclusively on Fargate, your application or your service exclusively on Fargate, you may want a placement constraint that looks a little bit like this. Here we are looking for an attribute set by the ECS agent called CPU architecture. And we're making sure that it matches the value ARM64. By setting this in your task definition, ECS will make sure to launch this task only on an ARM64 or Graviton instance. Similarly, if you're running your ECS task on Fargate, all you need to do is set the requires compatibilities field to Fargate, and then set the runtime platform as shown here. You create a new key called runtime platform, and you set the subkeys operating system family to Linux and the CPU architecture to ARM64. There's no need to set a placement constraint for running containers on Graviton. As with ECS, with EKS, the control plane is also architecture independent, and both x86 and Graviton EC2 nodes can join a cluster. If you want to route specific pods or deployment to Graviton nodes, you can easily do so via a node selector or node affinity, which I will show in the following slide. And the cluster autoscaler is also architecture aware. Carpenter which is a autoscaler, a node autoscaler for AWS, was recently announced in reInvent 2021. And it can provision nodes just in time for the fastest scale out. Carpenter is architecture aware and will immediately provision Graviton nodes that closely fit pods as soon as they're launched if additional nodes are needed. Unlike Cluster Autoscaler, Carpenter actually takes advantage of our EC2 fleet technology in order to launch containers extremely quickly and highly concurrently, often in 30 seconds or less. I encourage you to visit to take a look at Carpenter, and I'll provide a link for that later. If you need to route a pod to a Graviton instance, the best practice is to use a node affinity in your pod spec. You can see an example of what a node affinity looks like here. Here, I've declared a node affinity with a term of a match expression that matches on the well-known key kubernetes.io/arch with a value of ARM64. This makes sure that the pod is routed only to a node that can run on ARM64. Both Cluster Autoscaler and Carpenter are aware that when a pod is launched with this sort of affinity to launch a new node if necessary, a new Graviton node specifically if necessary. Alternatively, you can use the shorter but less preferred syntax of node selector in your pod spec. Here, you simply set node selector of kubernetes.io/arch or arc to ARM64. If all of your node groups are Graviton, you don't need to specify either a node selector or affinity. It will simply launch the Graviton node, and if you're assuming that your image is Graviton ready, everything will work just fine. If you have installed Carpenter, you'll need to add a provisioner to your cluster. You do so by setting a provisioner with a spec that has a requirement, and in this case, all nodes that are launched by Carpenter are ARM64. You can also have a cluster of nodes with different architectures by adding AMD64 to the values as well, if you like. At this point, I would like to show you a demo of what a multi-arc container build and release pipeline looks like. I'm going to be using the AWS console code pipeline and releasing a new change by making a change to my source code. And you'll be able to see the deployment as it happens. I have built 3 different demo applications, each of which is written in a language that's compatible with EC2 Graviton. And I've created build and release pipelines for each one of them. And I'll show you both ECS and EKS examples for these. The first one is written in Go, the second one is written in Java, and the third one is written in JavaScript and uses the Node.js runtime. And you can see here, I've got 3 different GitHub repositories, one for the Node.js demo app. You can see in the source folder the package.json file. You can see a little bit about what it looks like here. You can see, for example, that it shows the architecture as well when you click the info button. The 3 applications are very similar. The other one written in Golang, also presents a single page application which has information on the operating system and platform it's running on. And then the Java one, of course, does as well. You can see here there's like a Maven build file on a pom.xml. So you can see here it's written in Spring Boot and OpenJDK 11. So very, very, very similar. All right, so going back to our pipelines, you can see here what one of those pipelines looks like. You can see here the source stage that pulls from source whenever I make a new commit to GitHub. A build image stage, which contains 2 code build projects run in parallel, ARM64 and x86. The test stage, which actually pulls the image and then does some real tests against it. Finally, assuming the tests pass, the multi-arch manifest is produced, and then finally the deployment to ECS is completed. So I'll just go ahead and release a change here in the background so you can see what happens through code pipeline. This takes a few minutes to run all the way through, so I'm not going to spend too much time working on this, but you can get the idea here. What does that look like in terms of our deployment template? Well, I've written a module that's shared by all three stacks, and basically what this does is it's a sub-template, as it were, that builds the entire pipeline. You simply pass it a few properties, including the source repo, which is a GitHub reference, the name of the branch that will trigger a push, where the image repository is stored, which comes from the service stack, the ECS service stack, a code star connection, which is used to connect code pipeline to GitHub. This needs to be made in advance. Paths to the code build specs for all the different stages, including build and push, testing the image, creating the multi-arch manifest, and then performing the deployment. So what does that look like? And I have one of these each for all the different demo apps. We have our Java one here, our Node.js one here, and then here is the JSON template that has all the resources in it that gets called as a module that has all the different log, for example, the log groups, roles, build projects, code build projects, and the pipeline. So that's all. Those are all. So I'm able to share a lot of code, of infrastructure code for all these different pipelines. So what does that look like when it's actually succeeded? So if I take a look here, for example, at this deploy to ECS stage, you can see here all the information that code build has printed out through my build specifications, and I have a little make target called make deploy, which deploys it to CloudFormation. So if I open up this URL here, this points to a application load balancer, which can show you here. This is my Go and Vue.js version. If I hit info, you can see here, in fact, it is running on a Graviton instance. And so that's working just fine. And the same is true for my Java version. So if I go to the Java version here and I open up the code build output, you can see here, oops, that is not right. Let's try that again. Let's go to our Java pipeline here. So if I go to deploy and I go to details, you can see here the ALB URL. So go to that and you can see here the Java version. If I click on info here, you can see it too is running on ARM64 on ECS. You can see here via the execution environment variable. And then finally, taking a look at the Node.js version, it's the same thing. So if I click on that and I go down to the deployment stage and I open up the application load balancer URL here, and you can see here, here's my Node.js demo, also running on in EC2 on ARM64. So you can see here that my multi-arch image is getting pulled there. Let's take a quick switch over to EKS. So in EKS right now, I've got a few different deployments here. And I've got one for my Java demo app, my Node.js demo app, and my Vue demo app. So if I take a look at my Java demo app, if I take a look at, if I get the pod for it, and I output the YAML and I get the host name that it's running on, you can see here that it is currently running, on this this node here. So if I describe the node, you can see here, I'll just actually get a list of them here. that I've got two different nodes, and right now this one ending in 246 here is running on Intel. And why is that? Well, that's because I have specifically instructed this application to run on Intel. Let me just show you what it looks like when it's running on Intel. So if I get our ingresses here, you can see here that I've got my Java web app here running on this address here. So if I open this up, that's also it's an ALB ingress. So let me go ahead and open that up here. And you can see this Java app is actually running on AMD 64, which is x86 64. And the same is true for my Node and Go versions. So if I look at the Node version here, you can also see that it is also running in Kubernetes on an x86 instance. And then same thing with Go, as you would expect. So if I open this up here, I do an info on it, you can see here it's running on x86 as well, also in Kubernetes. So that is all wonderful. And let me show you why it's actually running on ARM64. So if I actually edit the deployment of this, you can see here in my pod spec, if I go to the template down here, that I've actually have an affinity requirement that says this must be running on in x86 instance, where kubernetes.io/arch is in AMD 64. So let's see what happens when I change this from x86 to Graviton. This is my Java dev app, just to make sure. So I'm going to go ahead and edit that in place. And what it's going to do is it's going to actually create a new pod here. So you can see here that a new pod is pending. That's my replacement Java application. What's going to happen is Carpenter over here is actually creating a new ARM64 node here to make room for my rescheduled pod. So right now it's actually waiting. The node has now registered, has come online, and is going to register itself with the control plane. So Kubelit's going to go ahead and start, say it's ready, and then once it's self-registered with the cluster, then finally the pod over here will be able to be scheduled. So you can see here now it's in container creating state, and it's being scheduled onto the replacement node. Once that's done, and the container has started and has registered itself with the load balancer, we'll see the old generation of the pod terminate, and then we'll be able to go to back to the demo app and see that the architecture has changed. So that'll just take about 30 more seconds or so. So let's take a look at the application here. So let's go to our Java demo app. Still running AMD 64 at the moment. And it looks like it's now running, and the old version is in terminating state. So let's just give it another second. It'll say bad gateway for just a moment, but oh, here we go. Now you can see that the task has been replaced to a Graviton instance. And of course, we can do the same with any of our other applications. So my Node.js app currently still running on x86. And if all I do is go ahead and replace the affinity so that it is also running on, oops, that's the wrong one. Let's try the Node.js one. So if I go down to my affinity, I change it to ARM64, the same thing will happen. So if we take a look at the Node.js one, you can see Since we already had capacity for that one, because Carpenter launched a node with some extra space in it, you can see here that it's already replaced the Node.js with a new one. So if I go over to my node one, it's currently x86-64. Let me just create a new version of it here. You can now see it's also running on ARM64. Note that we did not change, if we go to the deployment, we did not change the image at all. We were able to switch between x86 and Graviton without changing the image. All we did was change this from AMD 64 to ARM 64. So we just substituted this. And if you actually supply these two values, and that means that the image can actually run on either of these two architectures. And Carpenter today will actually prefer Graviton, no matter what the order of the list is. It could be, you could put x86 first, or you could put ARM, but Carpenter will actually prefer to launch the Graviton instance because it saves you money, as long as the node selector allows both. So this marks the end of my demo, and I hope you found it to be interesting. Next, I'd like to talk a little bit about observability on Graviton. There are many different observability providers that are Graviton ready today. This includes Amazon CloudWatch, Splunk, Honeycomb, Datadog, New Relic, Sysdig, and also agents by FluentBit, Vector, and Logstash are all available for ARM64. So if you're using any of these observability providers, you can begin migrating to or adopting Graviton today. And you can do so with confidence that your observability and telemetry data will be able to be collected and analyzed, just like any x86 instances you might have. Finally, I'd like to offer a little advice in terms of best practices when you're deploying and using containers, Graviton containers in AWS. First, you'll want to come up with a migration plan. Because not every, although many workloads can be easily migrated to Graviton, not everyone can. And you want to migrate in a way that is going to be safe for your customers and will minimize any sort of unavailability or downtime that might occur. You'll also, of course, want to in your tests look very closely at the metrics to make sure that performance is as you expect. With Graviton, we expect performance to be even better than on x86, but we also think it's important that you verify and make sure that that's the case. And if you see any performance regressions, please reach out to your AWS account team or file a support ticket so that we can investigate and make a determination as to the best next steps for you. We recommend that customers adopt modern DevOps practices. This includes automated testing, building, and releasing. This helps make sure that you can deploy to Graviton and adopt multiple architectures if necessary with confidence. That there will be no regressions, and that the deployment process will take place smoothly and safely. The other great thing about adopting DevOps is that it allows you to lean on infrastructure as code. It adds stability to the overall build, release, and test process, and allows it to be reproducible on multiple architectures. As I said before, you should run the same tests on Graviton test instances that you run on x86 test instances. Although we expect that tests will usually pass because Graviton does not force any sort of application level changes. It's always best to make sure because we don't want, it's important to avoid the unexpected. As I said before, we recommend decoupling application builds and deployments using infrastructure as code. And so we recommend using pipelines to build applications, and we recommend pipelines for doing deployments. We recommend, however, deploying your infrastructure separately. So things like VPCs, clusters, etc. Keep those separate in separate stacks from your application builds. I recommend biasing towards serverless compute wherever possible, particularly Lambda and ECS Fargate, which is already ready, both of which are already have options for Graviton. These improve your security and scalability greatly, while allowing you to eliminate the toil of managing EC2 instances yourself. Finally, I recommend, if you're running EKS, take a look at Carpenter. Carpenter is our newest amazing technology for provisioning EKS nodes just in time, allowing you to save money and be extremely flexible with instance types. And then here are some links you can explore to further learn about all the topics that I discussed today. These include the Graviton Getting Started Guide, AWS Containers blog, our Containers Roadmap, a list of Graviton-ready partners, and the open source Carpenter node provisioning system. The Graviton Getting Started Guide in particular provides deep technical information around all aspects of AWS Graviton. Our engineers update this weekly to reflect the latest information available as we learn more from our customers and our own research as well. And we provide a lot of useful and actionable advice there about all sorts of application environments and the right low-level tuning that you may or may not need. We also provide advice about which are the best libraries and which are the best runtimes for getting the best experience out of Graviton. Thank you very much for attending this session. I hope you enjoyed it as much as I did. Again, my name is Michael Fisher. You can find my email address here, and you can also follow me on Twitter if you'd like. Thanks so much for attending.